Hi, everybody, and welcome to our presentation of Internet of Things-based Vehicle Control System, which is also IoT, VCS. My name is Jennifer Bernert.
My name is Victor Gutierrez-Diaz.
And I'm Douangmanivong.
I'm Mckelvie.
I'm Phuong.
Here are the topics that we will be covering in our presentation. The first one is project motivation introduction. Next will be the features of the project, which is broken down into multiple parts. The first is RC car overview, then simulator overview, application programming interface, also known as API, live camera feed, driver drowsiness detection, neural network-based sign recognition, haptic feedback sensors, and then we will have a demo of the car, and then we will have a summary/conclusion.
Now to start and go over our project motivation introduction and why we took on this project in the first place. Due to the recent pandemic of COVID-19, we wanted to come up with a solution that would combat the issue of the social distancing guidelines. Our project scope was a little bit different in the beginning, but we found a good way to pivot and apply it to the current circumstances that we're facing. The creation of a remote piloted vehicle that could deliver necessary medical goods and other essential items was born from this current motivation. Through the use of our different items with the RC car API, the simulator system, and as well as a driver drowsiness detection implementation and other necessary sensors, the overall motivation and vision became a reality. Simply put, we wanted to create a way for contactless delivery in hospitals or other affected areas to be able to still take place, even though we are supposed to be quarantined and social distancing. All around, all the individuals could stay safe and healthy while still performing important and necessary duties to ensure the health of others.
So for the RC car overview, we opted to implement the vehicle using a self-built RC car. So the motivation for this for the RC car is that we can focus primarily on individual components of the system rather than implementing it using a real-life vehicle such as a go-kart or an actual vehicle. So instead of that, we chose an RC car so we can focus on primarily sending control signals over the cellular network, creation of a portable system because we want to be able to scale it up to vehicles eventually. We also wanted to focus on live camera feed, driver drowsiness detection, and other safety systems. And the reason why we did a DIY RC car instead of buying one is to allow us to fit everything we needed onto a chassis instead of having to spend unnecessary money for something that we would have to modify in the end.
So VRX Simulator is one of the necessary tools we had planned on using to implement the device to have our operator have a specific controller to give it a more immersive and visual experience, to add more layers of situational awareness when it comes to them driving around certain scenarios. But due to the whole COVID epidemic happening, we weren't really allowed to go on campus. So we found a way to kind of adapt to this. What we decided to do is adapt our code that we had for the simulator and have it take direct input devices, which are basically generic gaming controllers that can be found anywhere on the market. This kind of had a way to help us out in two methods. So this helped us out, kind of set the project up to be more financially feasible or cost effective for any place that wants to implement this actual project. And not to mention, it made it much simpler to get the actual controls out.
All right, for the API that we're using, again, it's direct input. This is where we use the controller and interfacing with the library to capture all the controlling data. This is using a C++ library off of Windows. And what we do is control our steering, gas, and brakes using this direct input controller capture. And then how we send over the controller commands or data is through UDP communication. The reason why we're using UDP communication is because it's a real-time data transfer, and we don't really need to wait for the handshake. We just rather send a bunch of controls straight into the cart, so it doesn't need to wait for a response, so therefore causing any other delays. And basically, how we communicate from the cart to other computers or other controlling units is through a VPN hosted by a Raspberry Pi. what we use is a PyVPN to create a server for us to connect to each individual person, either me or Casey, Victor, who can just log in to control the cart, but they have to have an authorization configuration profile in order to log into control. Therefore, it gives us a security aspect to make sure our cart is fully secured.
So for the live camera feed, well, obviously the system is meant to be piloted from a remote location. So the most reasonable thing is to focus on the live camera feed. And it's necessary to implement remote piloting, but it's also necessary to have high fidelity and low latency, which is something that we tried to prioritize. However, given the certain constraints that we had with using a Raspberry Pi, it was not fully realized. So the way we implemented it in our system is to use a Raspberry Pi Motion server. And Motion is an application that hosts an internal server for the camera feed. And by using port forwarding on the modem, we can allow connection to the server as long as we have the correct credentials from any remote location. And from our testing, we have around an average of 1.5 seconds of latency, which is really not ideal because we want to get as close to real time as possible. However, this does pave way for the future implementations to improve the feed by decreasing latency and also looking for ways to improve the fidelity of the camera equipment.
Now, with a pilotless remote system, safety is still our top priority. And with the implementation for the COVID-19 pandemic, a lot of the drivers that would be controlling these cars for deliveries would be working late nights, early mornings, long shifts, due to the necessity of the items. So the possibility of falling asleep behind the wheel is still apparent. So we wanted to implement a driver drowsiness detection system. This is to ensure the safety of the driver and the other individuals coming in close contact with the vehicle. And this is why this system was implemented. With workers taking on the longer hours during this catastrophic time period, falling asleep behind the wheel could definitely cause damage to the car, the items, or hurt individuals that are on the side and interacting with the car. So to explain the overall implementation, when the driver's eyes are detected as falling asleep, as seen in the pictures on the right, the car is stopped and an alarm is played to alert the driver and help get them awake and from being asleep. This stops the car also in its tracks, so no problems are caused. This uses the camera system that watches the driver continuously and tracks the driver's face and their eyeballs. This then sends a message to the car, which in turn stops the movement completely, so no one is hurt and the goods are not damaged at all.
For the sign recognition portion, it is added to be a second set of eyes using the camera live feed on the car. The safety features of this is that when a stop sign is detected on the camera feed, the car will stop. As is with the extra set of eyes, it is an added vision for the driver because if stop signs are missed, there could be possible casualties. There could be damaged goods that are trying to be delivered and lives could be lost, which is not a good thing. The way that implementation was done is, like I said earlier, it utilizes the live camera feed, and then there are also onboard neural networks used on the Raspberry Pi that is on the cart. In order to be able to determine the stop sign, there is a library in the code that has a set of images, and then the code uses color contrast in order to determine the sign from the camera feed, and that can be seen from the green circles on the image and the stop being outputted on the right-hand side of the image. And a client-server model is used to send and receive the values to tell the car how to stop.
Following this is a haptic feedback system and vehicle positioning. So it's very important to let our operators know where and how the vehicle is positioned and how it feels, and to give them another sense of another layer of situational awareness to kind of add to their decision making when it comes to, let's say, driving down certain uneven terrain or being aware of where their positioning normally is as a car in the world around them. Right, so there was the one way we implemented this was using a accelerometer and gyroscope. that would take in about 100 samples per second and have that transmitted over from a Raspberry Pi over a modem through a wireless network using UDP protocols for transmission and having it sent over Wi-Fi. The significance of this data was to let, again, the drivers have some situational awareness and be able to make better decisions depending on where the vehicle may have been, how it was posted up, and what was around them. Given the fact that we weren't able to have access to the actual simulator system, other ways we could have used this data was to have a graphic user interface to display the actual positioning of the vehicle to give a better sense, even though the actual driver or operator wouldn't have the whole system along with them. This also lays a good groundwork for any future teams to use this information and have it develop further in the system once they get access to it. And following this, we'll be presenting a quick demo, and we'll be showing you that now.
So as you can see in the top right corner of my screen, I am running the simulator data collection from my house, which is connected via a VPN service over to Alan's house, which you can see in the top left corner. In the top left corner in the left window is the camera feed that Lucky implemented, and that is on the front of the car. And on the right side is our car overview, is the car itself. And in the bottom left of my screen, you can see the driver drowsiness detection, which I will start in a bit after demoing the movement of the car. And I am using a PS4 controller to send the data to the Raspberry Pi, which is hosting a server on Alan's side at his house, and will control the car. So I'll do a short demo right now and then show the driver drowsiness detection system working as well. So here I'm going forward, it is setting the values. I'll stop, I can adjust left and right with the turning. And this is all happening remotely. And I'm turning, and it is all being fed live to the camera view, and I'm viewing it from my house as well. So now Alan's going to reset the car to the original position, and I will launch the detection system. When it detects that I'm falling asleep, it will automatically stop the car for 10 seconds and make it so I'm unable to move. And then after that 10 seconds, I will be able to move again if I am once awake. So now I will launch this. Loading right now. So you can see that the system is detecting my eyes, and so it's detecting my eyes, and I will then control the car. Right now, I will close my eyes. Detects that I'm asleep, and it completely stops the car, and I'm unable to move it for a time of 10 seconds. So therefore, it is correctly working and being implemented. So we can show this again since it was 10 seconds later. I can move the car around. I will close my eyes, and therefore the car is stopped again. So overall, that is a short demo of our car working and the complete system. And this is the full data communication from my home over to Alan's. And this concludes our project demonstration. Thank you.
For future work on this project, this is part of the summary and conclusion. There will be changes to the car frame to support more capabilities for delivery, more areas to hold more supplies, and just a bigger car so that it is more noticeable and it is more efficient. And then there'll also be a voice system so that the driver can be able to talk to the customer or to whomever they're delivering to, so they actually know who it is coming from. There can be that little bit of human interaction, even though it is a car. Another one is an alert system so people can hear the car coming. This way, it's another safety feature, and people won't trip over the car because the car isn't exactly in the natural line of sight for somebody. So if someone is walking with a cell phone in hand, this way they'll be able to be alerted so they won't trip over any supplies. And if test tubes are being delivered, they won't be broken and contaminated and not being able to get tested. Some other additional safety features will be accidental collision protection. So if it's about to run into a wall because something is going wrong in the system, someone's not paying attention, it won't crash and protect what it's carrying. Another one is lane departure warning. This doesn't just apply to lanes that could be in a freeway. It also helps the car stay in a straight line, because if you are swerving, that could lead to an accident, and that is not good. Another one is object recognition avoidance. So if you're about to run into a tree, this is like, hey, you're about to run into a tree. Or if you're about to run over a water bottle or into a rock, any object that would be on the ground that the car could possibly collide with. Another is GPS capabilities, and this is just to be more accurate with the destination you're traveling to, and also to know about how long you're going to get to the destination, so you can let the end user know when you'll be arriving with the car. And that summarizes our project. Thank you so much for listening, and have a good day.